Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Ian Wong with us today. Hello, Ian.
Hi, everyone.
And Ian, where are you located at?
So I'm actually right now a staff scientist at the Space Telescope Science Institute in
Cool.
Baltimore, Maryland.
Very cool.
I started the position 3 weeks ago, so
Oh.
it's a brand new office
Very good.
life for me.
Very good. Very nice. And Baltimore, let's see, it is May 1st of 2024 as we record this. Spring is in the air in Baltimore. We got blooms. Is it going?
Yeah, allergies also. Yeah,
Well, that comes along with it for some people. Absolutely.
I'm better today than yesterday for sure. So
Do you suffer from allergies?
I do. Yeah,
I was going to say
ever
that's
since
why you
moving
brought
to
it
this
up.
area, yeah, it's been pretty notable, the increase in pollen. So.
Okay, very cool. And I'm in Phoenix, and we are definitely warming up to our summers. So we're going to hit the triple digits probably in another week, because when the power blaster will go on. So yeah, it's all good. And Ian, what do you like to do for research?
Yeah, so generically speaking, I call myself a planetary astronomer. My interests are in planetary bodies, both in the solar system and in extrasolar systems. So recently I am I've been working a lot on small bodies, particularly in the outer solar system, using James Webb observations.
Okay.
So trying to study their properties, the surface compositions. I've also been working a lot on exoplanet characterization, particularly using things like phase curves, secondary eclipses in photometry, and also spectroscopy to try and get at the heat transport on their surfaces, the composition of their atmospheres, and looking at sort of ensemble trends with data from tests, particularly in the recent 6 years. I've been doing a lot of test work.
Cool.
So yeah.
Okay. And that is going to bring us to this very awesome PSJ, Planetary Science Journal article. It is open access. It's the open access era, people. Go get a copy for free. JWST, near-infrared spectroscopy of the Lucy Jupiter Trojan flyby targets, evidence for OH absorption, aliphatic organics, and CO2. And Ian, take us away.
All right, thank you for that introduction. Yeah, so this paper is a very exciting work. Of course, it's not just my work. I've worked with a small team of experts. Mike Brown's the second author, and also my former PhD advisor at Caltech. Josh Emery, Rick Binzel, Will Grundy, Simone Marshy, Audrey Martin, Keith Knoll, and Jessica Sunshine. So they all contributed in a big way to help devise this observing proposal, as well as interpret the results. So they all had a very big role in bringing this project to fruition.
Good shout out. Good shout out. Okay.
Yeah. So of course my affiliations are a little bit outdated now, but I completed this work at my previous postdoc at Goddard.
Okay.
So this is work that I did throughout mostly 2023, when I was still a postdoc.
Cool.
So I guess jumping right into the abstract. So at face value, this is a JWST observations paper. It's based on a proposal, a Cycle 1 proposal, a GEO proposal, the PI of which was Mike Brown. This is also ostensibly a mission support program. So as the title says, these are Trojan flyby targets of the Lucy mission. So Lucy, to give a little bit of background, so Lucy is a NASA mission that was launched in October 2021. The main objective is to carry out flyby study of 5 Trojan targets throughout the next decade or so. And the 5 targets that we looked at in this proposal and summarized this paper are indeed the 5 Trojan targets that will be visited by this spacecraft in the coming years. So much of the motivation behind this paper is to try and use the next generation capabilities of JWST to really shed some light on the detailed surface composition and properties of these objects, in preparation for, of course, the exquisite spatially resolved information that we will get from the spacecraft flybys.
Very cool. And when are those flybys scheduled?
So there'll be 4 flybys in somewhat quick succession in 2027, 2028.
Okay.
So I guess some more background here. So the Trojans are asteroids that are locked in a 1-to-1 mean motion resonance with Jupiter.
Yes.
So they're confined to the L4 and L5 Lagrangian regions within Jupiter's orbit. So these sort of lead and trail Jupiter by about 60 degrees in longitude.
Yes.
So 4 of the 5 targets are in the L4 swarm, the leading swarm. Okay. So the spacecraft will first do the rendezvous through that swarm and hit the 4 targets within about 14, 15 months. So really quickly do the first 4 targets. And then we'll actually go back to Earth, do another gravity assist, and then go out to the L5 swarm. About 5 years later, it will reach the final target, which is Patroclus.
Okay.
In 2033.
Cool. Wow. All right. That is great. Thank you for that background. Very good.
All right. So I guess we can move on to the introduction. So many of the listeners are probably not as familiar with the Trojans asteroids as I am. So these asteroids are very interesting because they are situated, as I mentioned, within Jupiter's orbit. So they're just outside the main asteroid belt that most people are familiar with. When we talk about asteroids, most people think about the main belt between Mars and Jupiter. So these Trojans are in a similar kind of region of the solar system. However, our understanding of their origin has been sort of a story in and of itself. So the early ideas were that they simply formed in the vicinity of Jupiter, and then as Jupiter grew into its full mass and isolation within the protoplanetary disk, it trapped these nearby planetesimals into the Lagrangian points. So that was sort of the classical picture of the solar system in general. But recent theories have instead posited a very different picture. So these models, often collectively called the Nice model, after the city where it was devised in 2005, these models posit that shortly after the dispersal of the protoplanetary disk, so once the dust and gas were dispersed and you had the planets orbiting in isolation, there was some dynamical chaos. There was an episode of orbital architecture restructuring that dramatically changed the architecture of the solar system. And in particular, it's thought that the ice giants, Uranus and Neptune, were essentially flung out, chaotically expanded their orbits into this broad reservoir of leftover planetesimals in the outer solar system. So these are very ice-rich, sort of proto-Kuiper belt objects.
There you go.
And indeed, these types of models have been devised to explain a lot of the dynamical excitation in the Kuiper belt. But a corollary of all these models is that this episode of dynamical restructuring destabilized the region around Jupiter. And what happened next was, during this whole process wherein the ice giants were expanding outward into the icy planetesimal disk, some small fraction of these objects were actually scattered inwards. They went on these initially very eccentric orbits, and eventually they got in close contact with Jupiter and were captured into the Lagrangian regions. This is a very drastically different picture than sort of the classical conception of
solar system in a solar system kind of model, right?
Right. So in this sense, the Trojans play a crucial role in testing our understanding of this early solar system history. By studying their properties, we're hoping to uncover some telltale signs that may point towards one or another hypothesis for the origin. So this is kind of indeed the motivation for the Lucy mission itself. It was really it was initially a decadal, one of the priorities in a decadal, and then eventually was approved as a Discovery class mission. So, so this whole underlying story is sort of what is motivating us to look at Trojans very intensely in the next few decades.
Very cool. Very cool.
So Trojans have been known for over a century, and the numbers of objects that we know now are past 6,000. And sort of, if you look in the second paragraph, it gives a kind of an overview of the past, our past knowledge, our previous knowledge of these objects going into the JWST era. So there have been numerous ground and space-based observations of Trojans over the past few decades, looking at the reflectance spectra, looking at albedos and colors. And sort of the big breakthrough really came from the Sloan era. We got hundreds of photometric measurements of these moving objects in the Trojan region. And what we found was that the color distribution of these objects is not unimodal. They are all red, but they kind of cluster into these two different subpopulations. I gave them the name less red and red. They're perhaps
very Most, yes.
It tells exactly what you need to know about them, right? So they're all these objects are dark. They have notably very low albedos.
Yes.
They are mostly featureless throughout the optical and the infrared, but they have these two types of red slopes, kind of two flavors of surface colors.
Okay.
And that's sort of driven our attempts to understand their origins in a sort of an extra dimension, trying to explain not only where they came from, but how these two different subgroups arose.
Right.
So that's another one of the motivating factors for this particular set of observations. Cool. And also the target selection for the Lucy mission as a whole. If you go to table 1, table 1 gives you sort of a quick overview of the properties of these objects. You see they range in diameters from 20 to 150 kilometers. They're all low albedo objects, under 10% albedo in the optical.
That's a geometric.
And the targets sample both of the colors of population. So we have 3 less red objects and 2 red objects.
Yeah. Distributed between the two. Okay.
Yeah. So the target selection for the mission was very much to sample the whole range of objects, from the small to the large, different colors, as well as crucially different binary and collisional histories. So the first target on this table, Patroclus, is actually a binary. It's a binary consisting of 2 near equal size components.
Okay.
So there are 2 objects that are locked in a mutual orbit around each other. And to our knowledge, they have the same colors and properties. But when we have the spacecraft flybys, we'll be able to study them individually in great detail. So the selection of Patroclus was very much motivated by its unique binary nature.
Yep. Cool.
The second target on this list, Euripides, is also notable. It is the only collisional fragment among this small group of objects. Collisional fragments are the results of a catastrophic disruption of a larger parent body. So essentially 2 objects collided and they broke up into a swarm of smaller objects, and they create collisional families, objects that are all sourced from the same parent body. And Euripides is the titular and largest member of its family. So including Euripides was also important because it allows us to see the effects of this surface regeneration, this exposing of inner material due to collision. And by comparing Euripides with the other objects, which to our knowledge have not encountered or experienced any catastrophic disruption, we can see this sort of differential evolution of their surfaces. And that gives us another angle by which we can understand what's going on in the Trojans.
Cool.
So again, so this relatively small list of targets, just 5 targets, they really kind of covers every part of the parameter space, so to speak, of the Trojans.
Some very interesting. Yes.
Yeah. All right. So I guess let's jump into the observations. So this is as I mentioned, a cycle 1 general observers program, with the PI being Mike Brown. So these observations use the NIRS-SPEC, the near infrared spectrometer, on James Webb, specifically using an integral field unit. So integral field unit essentially is an imaging spectrograph where you have a field of view in which every pixel contains the full spectrum.
Yes.
So it kind of encompasses both spectroscopic information and spatial information.
Very cool.
Now, I will note that none of these objects are resolved. We don't actually resolve any of these objects at the pixel scale of NIRS-SPEC. So we're not actually able to look at different regions of the surface.
Okay.
But nonetheless, this mode is sort of the working course of especially solar system observations of asteroids and other small bodies. It's a very efficient way of, powerful and efficient way of observing these faint objects. So
nice.
I've worked on a lot of these observations, not just in this program, but in other programs. And, you know, it's a very powerful tool and the bread and butter of our small body work. Very cool. Yes, these observations were taken throughout 2022 and 2023. And, you know, there's a sort of a detailed walkthrough of the data processing methodology. So a lot of details there that I probably leave to the interested reader to look into. But I think I wanted to bring out a particularly important point, which is the way we extract the spectrum. Okay. So again, so as an IFU, integral field unit, each wavelength comes with a full field of view. So you're essentially doing photometric extraction per wavelength, unlike a normal spectrograph where you have a dispersed traced, you know, a strip of spectrum where you extract around. You're really looking at images at each wavelength. Yeah. Basically. So the technique we devised using utilizes the optimal photometric extraction technique. So instead of simply summing up the flux in an aperture, we are fitting a template to the source's shape on the detector. So essentially we are doing a least squares fit where we have some model that simulates what the shape of the target should look like on the IFU slice. This is called a point spread function, of course. And we're fitting that to each slice, which really beats down the noise, the jitter in the spectrum. You're able to get much higher signal to noise by doing this. And this is really crucial, especially when we get to longer wavelengths where the intrinsic signal to noise can fall quite severely. Right. And by utilizing this point spread function fitting technique, we're able to really bump up the signal to noise and look at these very, very small minor features. Nice. This is a technique that developed by Mike Brown and me for use not just in these observations, sort of across the board throughout the JWST cycle 1 data sets for small bodies. So I think this is a very powerful technique that I've used many times, and it was really a key to enabling a lot of the science that I will get into in the following discussion. Very cool. So I guess that's sort of the overview that I wanted to give about the methods. All right, so I guess we can just jump into the results, or at least the spectra. So in figure 2.
Okay, let's go to figure 2. Spectra.
There's 2 panels here. So on the left is essentially the raw extracted spectra of these objects. So these are in irradiance units, microjansky in this case. So there are a few points I wanted to point out. The first is that there are 2 different spectra here. There are 2 spectral gratings that we used. They're called the G235M and the G395M. So they cover sort of different but overlapping wavelength ranges at a spectral resolution of roughly 1000. And so this is the medium resolution mode of the NIRS-SPEC instrument. There's a low resolution mode, the prism mode, and a higher resolution mode with the H grating. So in this case, we used 2 of the medium resolution gratings to cover the range between 1.6 and about 5.2 microns. Okay. So here you see all 5 irradiance spectra plotted together. And there's a couple features of note. All of them steeply drop off with increasing wavelength at the left end. So this is simply the solar spectrum trailing off, right? This is all reflected light primarily. So we're seeing the reflected solar spectrum dropping off in intensity as you go to longer wavelengths. And this transitions to a thermal tail. So this tail at the long wavelength that goes up, that is the onset of the object's own thermal emission. So this is essentially the black body emission coming off the surface of the bodies. So you have both of these two components in this spectrum. So the first step we needed to do, because we're mostly interested in the reflectance spectrum. Right. So what we did is we used a thermal model that has been applied for many decades to small bodies observations. We use a thermal model to remove this thermal tail. So this so that gets rid of the thermal emission component from the objects themselves. Correct. And then we divided what's left by a solar standard spectrum. So to remove the wavelength dependent incident flux, we divide by a G-star spectrum. Correct. So details of exactly how we did that are in the paper. If for follow-up questions, we can get into the details if you're interested. But suffice to say that these two processes result in the right panel here. So we remove the thermal component, remove the solar spectrum, and we get the result, which is the reflectance spectrum. And this is sort of the starting point of our analysis is in the right panel here. So I've compiled all 5 of these reflectance spectra here in this plot. They are sorted by from bottom to top in order of increasing optical spectral slope or redness, so to speak. So as you go from Euripides to Lucas, you're increasing the redness of the object. Less red, more red. Yeah. So right away we see a few interesting things. So they're certainly not featureless, right? There's features here. So much of the rest of this paper is a very systematic deep dive into each of the features we see in these spectra. Cool. So the first of them is this broad feature from about 2.7 to 3.4 microns. It's kind of a bowl-shaped spectrum, spectral absorption that you see primarily on the less red objects. So the bottom 3 show this sort of bowl-shaped broad absorption. I'm with you. That's right. I'm with you. So that's the first one. The second one, which in contrast is primarily expressed on the red objects, is a narrower feature around 3.4 microns. So sort of a triangular shape absorption around 3.4 microns. That's feature 2. And the third feature, which is probably the most special in my mind, is only on Euripides, the bottom target here. And this is at 4.25. You have a very, very distinct absorption centered around 4.25 microns. So those are the three features that we talk about in this paper. 1, 2, 3. Gotcha. I'm with you. Yeah. So already we see sort of systematic differences between the less red and red objects. Even just qualitatively looking at these spectra, the less red objects are the ones that have the deep, raw 3-micron feature, which the red objects more or less lack. On the other hand, the red objects have that 3.4 feature very distinctly, being their most characteristic absorption. And then with Euripides, which is again the collisional fragment, the one collisional fragment in this set of objects, Euripides is the only object that shows this 4.25, this third feature at 4.25 microns. Okay. All right, so I guess I'll just dive into each of these features in sequence, starting with the 3-micron feature. Okay. So, the first thing people do in our field when we look at spectral features like this is we do a basic quantitative analysis. So in table 3 here gives the quantitative band centers and depths that we derived from fitting different functions to these absorption bands. So all of these processes involve removing the continuum, so the background shape
Yes.
slow monotonic background shape of the spectrum, and then fitting either a Gaussian or a polynomial to the band profile, determining where the minimum is, that gives you the center, and the depth relative to continuum gives you the depth. So,
yes.
so we did this systematically for all the objects
Cool.
in our sample at the 3 different features. And so table 3 gives you just kind of the overview of what we found. And really, this is just to put numbers to a lot of discussion I just had about the qualitative comparison. You see in the first columns is the quantitative results for the 3 micron band, and you see Patroclus and Euripides having much stronger, much larger depths in preliminary as well.
Significantly, yes.
Yeah, compared to the red objects, Oris and Lucas. Right, so just puts into numbers what you can kind of see by eye.
Spectra.
Yeah. All right, so so then let's dive right into the 3 micron band. So the next subsection in this paper kind of gives you, actually, we're already kind of scrolling through it. I think we can stop at this figure here.
Okay, let's stop.
Figure, what is this, 3 now?
Yes, this is 2.5 to 3. Yeah.
Yeah. So figure 3 here. So how do we kind of interpret these results? So there's several approaches you can take. One is to try and do a spectral model, right? So you take a bunch of these lab spectra or optical constants of components that you think are on the surface.
Yes.
You do some fancy mixture, looking at the optical path. You construct a surface, model surface.
Yes.
You model how the light interacts with it, and then out comes some model, and then you could do some iterative fitting and try to see what the fractions of the different components are.
Right.
So that's great. That gives you a lot of nice juicy numbers that you can say about what percentage of this surface is A, what percentage is B, what the grain sizes are. So that's great. But for a lot of these spectra, it's ambiguous exactly what is going on. Like, what is the species that is responsible for example, this 3 micron feature? There's a number of possibilities. Furthermore, all these models, spectral models, have a lot of assumptions. So you are sort of beholden to the caveats that you drag along the whole way. So the approach we took instead in this paper is to do more of a qualitative shape-based comparison with analog spectra of other objects that exist in the solar system. So kind of backing up to the initial motivation, why we're interested in Trojans is to see where they came from. And one way to attack this problem is to put them alongside other small body populations in the solar system.
Good.
That's the approach we took in this paper. So this is exemplified by this first spot here in figure 3. So the top panel, this is once again the reflectance spectra of that region. This time I've removed the continuum. So the continuum is flat. And that really accentuates differences in the positions of the bands and the depths.
Yes.
And in the bottom 2 panels are a range of other objects. So in the middle panel, we have a number of main belt asteroids, Ceres and Pallas and Themis. So these are all main belt asteroids. And 67P is notable. It's targeted the Rosetta mission. This is actually a Jupiter family comet. So it's an active object. But likewise, in the general vicinity, right? So these are in the kind of orbiting the main belt asteroid region. So a few things stand out right away. The first and obvious, hopefully, conclusion from looking at this plot is that these look nothing like the Trojans, right? Qualitatively, if you look at the Trojans above and try to match the bands and the shapes, they're completely not alike.
Okay.
What's really notable?
Go ahead.
Yeah. So a particular thing to notice is what's kind of marked by this vertical line here. This vertical line more or less approximately shows the left edge of that 3 micron band in the Trojans. Look at the top panel. That inflection point that denotes where that band starts is around. This is around 2.7 microns.
0.7. Yes. Okay.
I believe it's 2.7.
Okay.
In contrast, if you look at Ceres, Pallas, and Themis, they have a feature there, but the left edge is not only much sharper, but it's also shifted to shorter wavelengths. The left edge of that per feature in their spectrum is at a different wavelength, closer to 2.6.
Mm-hmm.
So there have been lots of works looking at interpreting what is going on the main belt asteroids. So the general consensus appears to be that features that have this shape analogous to what we see on Ceres and Pallas, that feature that comes to a minimum around 2.7, that feature is a hydrated silicate feature. So these are silicate species, so refractory species that have at some point in the past interacted with liquid water. So there's a whole field looking at, what this means about the formation of these objects, which I won't get into, but suffice to say, these are hydrated silicates on the main belt asteroids that I've shown here. And crucially, we don't see the same narrow 2.7 feature, 2.7 micron feature on the Trojans. So we are able to more or less exclude these pure hydrated silicate components on the surface of these objects. So that's kind of the first big result, is that this contrast between the Trojans and the main belt asteroids I've shown here shows that the silicate nature of the silicates on the surface is fundamentally different.
Correct.
Yeah.
Beautiful.
Yeah, I mean, there's a lot of caveats to this interpretation. Ceres and Pallas are much larger than the Trojans. They're kind of in a different size range, so could be all sorts of things going on there. But suffice to say that they are not analogs to the Trojans, and certainly had a different evolutionary history. So Trojans do not share the same evolutionary history as the few main belt asteroids that I've shown here. The comparison with 67P is also interesting because there's an additional feature that you see in that spectrum around 3.1 microns. So there's that dip around 3.1. You see it actually in Ceres as well. Ceres and Themis also show this 3.1 micron feature.
It does.
Yeah, so this second dip is a little bit ambiguous in the literature. So it's been alternatively explained by fine water ice frost or an ammoniated clay. NH essentially have some sort of refractory species that has NH in it. So nitrogen hydrogen is an NH stretch feature in this on the surface. So you see those in 67P, Themis, Ceres, but crucially on the Trojans, we don't have a distinct feature at 3.1 microns. Instead, we have this much broader feature that spans that entire wavelength range shown here. Yeah, so we're unable to say that we have this separate component that's responsible for this 3.1 micron feature on the Trojans. Unlike the case of some of the other objects I've shown here, like 67P, where that has been able to be interpreted through modeling to be, in this case, an NH stretch, ammoniated clay. So I guess in short, this first and second panel comparison gives a result that says the Trojans, we aren't able to find a good analog for Trojans among main belt asteroids or other objects sort of roughly in the main belt asteroid region.
Cool, I'm with you. One question: what are the data points here for Themis?
Yeah, so there's two sources here. The green dots, I believe, come from IRTF. So this is ground-based observations from IRTF. And all the solid line at Themis is from the Akari spacecraft. Actually space-based observations. Likewise for Ceres and Pallas, those are Akari spectra. In the case of 67P, that's from Dawn. The Dawn mission, the Rosetta mission. Sorry, wrong spacecraft. That's the Rosetta spectrum.
Cool. Thank you. Okay.
So the last panel here is a different object. So this is 238P, and this is actually a JWST spectrum. So we're comparing like and like for the first time.
Nice.
So this is a JWST spectrum of an active main belt asteroid. So this is it's an asteroid. This was a main belt object, but shows periodic cometary activity.
Yes.
So
Yes.
you may be wondering why there's a gap there at
Uh-huh.
2.7. That's where the water vapor emission is. So this active object has these gas emission peaks due to water vapor at 2.7. Right. I've trimmed those here so that they're not distracting. They're interesting, of course, but that's not what we're looking at. Yeah. So what's notable about this object is that to first order, this absorption band is kind of similar to what we see on the less red Trojans. So if you kind of zoom out a bit,
right, like here, it's kind of here.
Yeah, it's the closest thing we've seen, right? It's sort of the closest thing we've seen.
Agreed.
Yeah. Unfortunately, due to the water vapor emission, we don't really have a good handle of where that left edge is. But broadly speaking, this wide feature spanning the 2.7 to 3.5 micron range is somewhat akin qualitatively to what we see on Trojans. Yes. So what could this mean? Well, in this paper, we don't really speculate exactly what this sort of first order similarity means, but these are active objects. This is a much different size range. 238p is a very small object. So it's an interesting comparison.
It is. Thanks for putting that on there.
So that's one angle. So that's one side of the story for the 3 micron. So so we talked about the main belt asteroids. How about the Kuiper belt objects? So as I mentioned in the beginning, the current understanding of Trojans is that they may have arose from the outer solar system. So these could be essentially inward scattered KBOs, Kuiper belt objects.
Yep. So
why not compare them with KBOs, right?
Okay, let's do that.
Kind of an obvious avenue to pursue. So indeed, in the figure 4, we did just that.
KBOs. Okay.
Yeah. So this comparison was really only made possible by a very large Cycle 1 program. So there was a Cycle 1 geo program that observed more than 50 Kuiper belt objects.
Okay.
And we used data from that program, process it through the same techniques that we did for the Trojans, to get these comparison spectra we see here. Okay. So so I've only showed in the top panel, I'm only showing the less red Trojans. Because those are the ones that show the deep 3 micron.
Yes.
And the vertical scale, of course, is stretched a lot more. So you really, really see how significant that dip is. Yeah. So then the bottom 2 panels show 2 pairs of objects. So the middle one, those are centaurs. So probably another somewhat unfamiliar term for people outside of the solar system context, but centaurs are inward scattered KBOs, recently inward scattered KBOs that are on orbits that intersect the giant planet region. So these are objects that, orbit. They have semi-major axes between that of Neptune and Jupiter. Yeah. So they're kind of just wandering around the giant planet region. Due to that, their orbits, they're unstable. So on 1 million year timescales, give or take, they are ejected from their orbits due to a close interaction with a giant planet. Centaurs are useful because by virtue of their smaller heliocentric distance, we're able to see smaller objects with the same amount of telescope time. So those Okerho and 2003 WL7 in the blue and green here are examples of centaurs that were observed by this large Cycle 1 program.
Interesting.
The bottom panel are just KBOs, regular KBOs in the Kuiper belt region. Yeah, so those are just 2 KBOs from I didn't really give too much thought in selecting which ones to show. There's so many of them to choose from.
Good. Just kind of a random selection.
Yeah, things that with good signal to noise and show a lot of things. So there's a few takeaways here. The first is that the KBO spectra show a lot more stuff. Right, there's a lot more going on there. You have this little peak, right, where your cursor is. That peak at 3.1. That is what we call a Fresnel peak. It's a scattering, a result of scattering of light within a crystalline water ice structure.
Oh yeah, okay.
So this is telltale sign of water ice,
Okay.
specifically crystalline water ice on the surface.
Nice.
Other signs of water ice include the 1.5 and 2.0 micron absorptions. Yeah, very clearly especially that red curve, the red
one. Yeah,
spectrum.
red one's really clear.
Yeah, it's very deep. Yeah, so all those features are water ice. So we know that these objects are rich in water ice on their surfaces. That's not that surprising. You know, they're cold. So ice. In the case of the purple spectrum, 2004 TY364, those little, right there where your cursor is, those are absorptions from CO2 ice. So carbon dioxide ice.
Okay.
Yeah, so that's an extra feature, an extra component that's there.
Cool.
Yeah, so those are kind of the extra little spectral information that's present in the KBO spectrum. So right away we can notice that the Trojans don't show a 2.0 micron feature. Okay? So the wavelength ranges overlap in that region, and we don't see any sign of an absorption at 2.0. And this is something that's been known before. There have been very, very concerted efforts to try and find signs of water ice on Trojans.
Okay.
Because if Trojans came from the outer solar system, they had to have ice there. Where is the water ice? Well, that's a big mystery. So, previous modeling works have placed upper limits on the water ice fraction on Trojans at something like 1 or 2%. So you're really not seeing any signs of water ice on the surface of the Trojans, which is a curious piece of the puzzle. Why is there no water ice? Well, we will get into that in a little bit later, but that's one of the big mysteries going into this observing campaign was can we find water ice? And we don't see any 2.0 micron absorption. So it seems like the story holds. The water ice, the pure water ice on the surface of Trojans has to be limited to a few percent at most of the composition.
Yes.
All right. So there's another dimension to this plot, which the y-axis scaling may not make this as clear, is that if you look at the KBOs and the centaurs, you look at the depth of that 3 micron band.
Yes.
You can immediately see that the centaurs have shallower absorptions. The absorptions at 3 microns are shallower than the case of KBOs.
Yes, true.
Yeah. What's particularly interesting is that if you compare the 2 centaurs next to each other, just do the pairwise comparison of Okerho in 2003 WL7 in the blue and green, you can immediately see that Okerho has a shallower absorption at 3 microns.
Yes.
Simultaneously, Okerho also has very, very little sign of the water ice. Right? The 2.0 band is very, very muted.
Weak.
So what's interesting, if you look at the orbits of these 2 centaurs, is that Okerho is among the closest centaurs that we know. Right? It has an orbit that is just beyond Jupiter's orbit, sort of between Jupiter and Saturn. Whereas 2003 WL7 has a much larger orbit, it's a much larger semi-major axis. So you can potentially argue that the heating, right? So as you get closer to the sun, you're getting hotter. This heating component may be playing a role in beating down the depth at 3 microns. So you can almost you can kind of trace your eye from the KBOs through the green and the blue spectra, and then down to the Trojans. You see a progressive attenuation of the 3 micron depth.
Okay. Yes. Yeah,
so going from somewhere like 60 to 80% absorption to down to 40% and 60% in the case of the green spectrum. Okerho, you're more like 20%. And then we get into Trojans, you're under 10%.
Yes.
Yeah. So this sort of qualitative trend, right? Again, this is a very
interesting
haphazard sort of. We just looking at spectra, and we're trying to draw a potential hypothesis here. We're saying, okay, centaurs are being heated higher temperatures than they formed. Right? They formed in the Kuiper Belt. They were recently scattered inward, and now they're being heated up.
Where they lost it somehow. Probably heating.
Now, this life cycle from the KBO to the Centaurs, that's exactly how we think Trojans would have evolved
Okay.
during this dynamical chaos. So they were initially out in this outer planetesimal disk. They were scattered inward, and they had this intermediate stage where they were on Centaur orbits, essentially Centaur orbits crossing the giant planets, and then they were eventually captured by Jupiter. So Centaurs are a excellent probe, a proxy for how Trojans may have evolved during this intermediate migration state.
Yes.
So one can imagine that Trojans were eventually captured by Jupiter, and they've been sitting at Jupiter's orbit for the last 4 billion years. So they're being cooked. So perhaps this thermal processing is responsible for this muting of the 3-micron depth. So this is sort of a shot across the bow, right? We propose this as a potential explanation that ties what we see with Trojans to this broader picture of their evolution, and ultimately trying to tie it to an outer solar system origin by this comparison with the Centaurs and KBOs. So this plot, I think this is probably my favorite plot in this paper, is that it suggests this sort of evolution. As you get warmer, your 3-micron band gets weaker.
Yes.
So exactly what mechanism is responsible for that? Well, we have some further speculation that we'll talk about in a moment, but there's could be heating or other things. But it suffices to say that this comparison suggests very strongly that there is some sort of linkage,
correlation. Yeah, absolutely.
Yeah, and eventually in the future, if we're able to really demonstrate this with a better understanding of the chemistry and the surface properties, that would be, that in my mind is a smoking gun. We really that really, if we can prove this, that would be essentially irrefutable proof that the Trojans indeed formed in the outer solar system.
Are KBOs. They're processed KBOs.
Yeah.
Very cool.
All right, so that sort of exhausts sort of what we talked about for the 3-micron band. So let's move on to the next subsection, which dives into the 3.4 micron feature.
Yes, 3.4. Here we go. 3.2 to 4.
Yeah. So if you look at the next plot, you see once again a collection of the continuum subtracted Trojan spectra. You have all 5 of them here now.
Yes.
This is, we're really zooming in here. So the scatter is quite strong, but even with the scatter, we can clearly see that Orus and Lucas, the bottom 2, show the strongest 3.4 micron absorption.
Yes, I'm with you. A little bit here.
Yeah. So so those are the red objects, the 2 red objects on our target list. And and they show the strongest absorption at 3.4. So what is that? What is going on there? What is responsible for this absorption? So thankfully, just like in the previous plots, we invoke qualitative comparisons.
Okay.
So in the bottom panels, show a couple analog spectra of other objects. These are all objects that I've shown previously. So in the middle panel, we have Themis series, naval asteroids, 67P, the Jupiter family comet, and they all show a 3.4 micron feature.
They do indeed.
Yeah, and then if you look at the bottom panel, those are our friends, Okraho, Centaur, and 2004 TY364, which is the KBO, one of the KBOs I showed previously. Right. And likewise, they also show a feature around 3.4, 3.5 microns. So these features like this have been studied for many years. And the current understanding is that this is due to organics. Okay. These are organic compounds on the surface. So what do we mean organics? Organics just mean something that has C and H. C and H. In this case, there's 2 types of organics. They're aliphatic organics and aromatic organics. This really just or aromatic organics have those ring structures like benzene. You have these rings of C, whereas aliphatics like ethane or propane have these chain of C. The carbons are in chains. So, the 3.4 micron feature is aliphatic organics, not aromatic organics. So this is a positive identification. So we have aliphatic organics on the surface of Trojans, similar to both some of the analog spectra that we see in the main belt and the outer solar system. Right? So this, at face value, this alone doesn't point either direction. We see organics all over the place in the solar system. But it allows us to identify this among these other comparison objects. So organics are notable in that they are often invoked in explaining why things are red. So if you irradiate organic ice, aliphatic organic ices like methane, ethane, in the lab, you get this kind of irradiation residue on the top that is dark and red. So there have been decades worth of experiments doing this, and the results of this have driven this interpretation that when the organics lend the redness to the object's surface color. So Oris and Lucas, the red Trojans, have a stronger 3.4 micron absorption, so more organics, therefore they're redder. So that's kind of the simple interpretation of that. And that's kind of what we propose in this paper. It's not a novel idea, certainly, but seeing the 3.4 absorption really clearly for the first time is a very big step. In really solidifying that perspective on the surface colors. Good. All right, and so last up we have the most interesting, I think, of the features is the subsection 3.3, which talks about the 4.25 micron band. And the title of the section already gives the game away. Is this CO2? Okay. Right. So I say CO2, right? But CO2 can be in various forms. And that's a very important angle in our interpretation is arguing how the CO2 is present on the surface. So if you go down to the last figure 6, once again, qualitative comparison. So the Euripides is the only object in our target list that shows this 4.25 micron absorption. Once again, this is it's a collisional fragment. It's the only collisional fragment in our target list.
It's been exposed.
So then in the middle panel, there's Europa and Ganymede. So these are the 2 Galilean satellites of Jupiter, right? And so these are all also JWST spectra. These are high resolution JWST spectra obtained during cycle 1. It's actually a pair of papers led by Samantha Trumbo that have published these results. So if you're interested in looking at that, those are,
check it out.
I believe they're in Nature, Astronomy, or Science. So and then the bottom panel you have one Centaur. So it's a 2003 WL7. That's Centaur. One of the Centaurs that I presented previously. And then in the red is a KBO. Again, one of the previous targets I've shown. So the first order takeaway, of course, is that these are CO2 features. We find them all over the place. So Galilean satellites, the Trojans, KBO, Centaurs. CO2 is abundant. Well, I would say abundant, but widespread.
There you go.
So how do we interpret this? So an important thing to keep in mind is sublimation temperature of CO2. So so CO2 starts to sublimate quickly at temperatures above around 90 Kelvin. So if you're hotter than that, CO2 ice, pure CO2 ice on the surface would not last very long. So the typical surface temperature in the Jupiter region is around 120. So immediately we can see that if you have exposed CO2 ice, it's gone. You can of course invoke some special caveat. But what if you just had an impact or a small exposure? But that's a special place, special time type of argument. But generally, if you have any amount of exposed CO2 ice, it's gone very quickly. And we're talking about weeks, months, not even years. We're talking about instantaneously, essentially. So Yeah.
Mhm.
Of course, this is not the case for the Centaurs and the KBOs. Those are safely at much colder temperatures. So we think that for the KBOs, the outer solar system objects like that, CO2 ice is indeed stable. So what we see on the surface is probably CO2 ice.
Yes.
So then the question is, so we can't have CO2 ice, pure CO2 ice on the surface of the Trojans. So how is the CO2 being expressed? Well, there are a few possibilities. And we're pretty agnostic to what it could be. We don't have the resolution to distinguish between these scenarios, but a few possibilities come to mind. The first one is you could have CO2 trapped in what we call clathrate, essentially a cage of water ice. You have water ice molecules in a crystal structure. And inside the empty spaces, you have these trapped CO2 molecules that are just sitting in that cage, right? They're kind of in prison, so to speak. Yeah. So clathrates have been simulated in the lab. There have been tentative claims of detecting them on places like Europa and other satellites in the middle solar system. So that's one possibility. You have
trapped
CO2 trapped in water ice.
Right.
Yeah. So previously, we talked about water ice. So while we don't see water ice on the surface of Trojans, we think that, if they indeed came from the outer solar system, they certainly have water ice inside.
Yep.
Inside there's water ice. They formed with water ice. So then, perhaps you could have CO2 trapped in water ice, giving this clathrate. And you look at lab spectra of clathrates, CO2 clathrates, they have a very similar shape. Broad. That's one possibility. The second possibility is sort of very amorphous. We call it bound CO2. CO2 essentially bound to something refractory, something that is not volatile, like silicates or other solid components. So not an ice, but a silicate or perhaps organic compounds or something like that.
Right.
So a similar species have again been posited as surface components on some of the Galilean Saturnian satellites. So that type of surface component where you have CO2 trapped in the structure of these more refractory elements is one possibility. So that's kind of a very broad term, but just to say somehow chemically bound CO2. So that's one way of affixing CO2 in a way that prevents it from volatilizing.
Right.
Is if you, this is another kind of more exotic hypothesis. It could be high carbonic acid. So you have water ice, you have CO2 ice. You shine lights on it, and one of the irradiation products is indeed carbonic acid, right? So it's a natural product of irradiation of water ice and CO2 ice mixtures. So one could imagine that primordially, in the outer solar system, these objects accreted with water ice and CO2 ice, right, at the cold temperatures. And, with the action of solar irradiation, some amount of that forms carbonic acid.
Yeah.
And carbonic acid is no longer volatile. It's not volatile like CO2 ice. So if you have the CO2 ice sublimating, whatever was converted to carbonic acid due to irradiation would remain.
Yes.
So that's one way of getting a CO2. I mean, it's not exactly CO2, but it's COO, right? That type of chemical component on the surface is in the form of carbonic acid.
Yeah. Interesting.
And so those are kind of the three possibilities that I gave for what could be going on with this 4.25 micron absorption on Euripides. But certainly more studies needed to try and really pin down what's going on there.
We'll come back.
So the last question is, why does only Euripides show this feature? Why do we not see this 4.25 micron band on the other Trojans?
Okay.
So here, we probably took the most obvious, at least to us, the obvious interpretation is that it has to be due to its collisional history.
Yes.
So Euripides is the only collisional fragment among our targets, and it is also the only one that shows this 4.25 micron feature. So perhaps the collision that Euripides experienced is why this 4.25 micron feature is expressed on its surface and not on the others. And this actually ties into the bigger picture of the evolution of Trojans. So once again, we're going to talk about centaurs. So centaurs, right? These are these giant planet crossing inward scattered KBOs.
Yes.
Some fraction of them are actually active.
Interesting.
They're comet-like. So by virtue of their heating, the activity is activated, and they experience outgassing. And what typically happens when you have these objects outgassing is that some of the dust and other refractory material is entrained in the outgassed coma, and some of it falls back on the surface. So what happens is you're essentially redepositing fine-grained dust and rocky material across the surface as a consequence of this activity. And perhaps this consequence of activity, this redeposition of dust, is covering up what would otherwise be visible in the spectra of these objects. So this simultaneously accounts for this 3 micron band being muted.
Yes.
It covers up the water ice that was there, and it would cover up any CO2 feature, right? If there was some sort of CO2 feature, you would cover it up by this
stuff. Sure.
Yeah. So then what happened with Euripides is, you had this collision, boom, it breaks apart into many pieces. And this catastrophic disruption essentially, it shakes off all this fine particulate, these little weak, dusty material, right? It kind of refreshes the surface. Right?
Recovers the surface.
So it does like spring cleaning, it cleans off all the dust, and you are seeing more of what's originally the surface, without this dusty layer. So perhaps what we're seeing here is that Euripides. So I think the interpretation we have is the CO2 feature is present in the interiors of all Trojans.
Fair, yes.
But they're otherwise covered by this dusty layer that has been deposited on the surface of the Trojans as a result of their previous thermal evolution. And in the special case of Euripides, this collision has reset the surface, and therefore it has allowed the CO2 feature to be visible, to be expressed again.
Cool.
So again, it's a tentative hypothesis, but it
follows.
Even be true. It's one of those things where it could be true. Like speculative stuff is always very fun, right? Because there's a lot of this analysis. This paper is just looking at the spectra themselves, quantifying the depths and trying to assign the molecular assignments to them. But what is the bigger picture? That's kind of where we had a little bit of fun. We tried to reconcile some of these results with kind of the broader picture that we're having about the Trojans' evolution. So
very cool.
So that's kind of an overview of the main results from a paper. We have kind of a number of lists of conclusions that kind of just hashes out all these points in a kind of summary form. So that's some of the big takeaways. Less red and red Trojans are different spectroscopically. The 3 micron OH feature on less reds. You have the organics primarily on the reds. And then Euripides is the special cookie that has that 4.25 CO2 feature. The CO2 is not pure CO2 ice. It's some sort of CO2 trapped in something else. Not sure exactly what it is, but it's notable that we see it also on a lot of Galilean satellites. So
cool.
It appears to be not uncommon in the middle solar system. Cool. So that's sort of the paper in a nutshell. I guess future work, or sort of intimated at this in some of the previous discussion.
Hang on to that future.
Okay.
We're going to come to that. Hang on to that. Let's do. Ian, that was awesome. Congratulations on a lovely piece of work here. Very nice. Thanks. And before I so rudely interrupted you, yeah, there are several potential avenues forward, given the published article that you mentioned. And so let's go ahead and push on those a little bit. What do you think it would take to firm up some of this evidence? Is there just more data? Do we need to look at more centaurs, more members of the middle and outer solar system? Is there other wavelengths that might be of interest? So yeah, where do you think we go with this, given the published article?
So there's a few avenues that I think are worthwhile pursuing. The first is to get more JWST data. Well, so specifically focused on what we think might be fresher surfaces. So the sort of last discussion we had about the 4.25 micron feature, the hypothesis that this is due to the collisional disruption of Euripides. So why not look for more of these objects, right? Similar objects. And indeed, there's a cycle 2 proposal led by Mike Brown, again, as a geo proposal that is looking at high albedo Trojans. Ooh. So in the introduction, I talked about how Trojans generally are very dark, very low albedo, but some previous observations have uncovered a small number of Trojans that have elevated albedo. Okay. They have albedos, above 15-20%. Wow. Significantly higher than the average of the population. Mm-hmm. So higher albedo immediately brings up the possibility that you're exposing something reflective, perhaps water ice, perhaps just ice in general, or breaking up some of those dark organic residues or something. There's a lot of things you can.
That's an interesting way. Yeah,
a lot of things you could do to make a Trojan brighter, right? So this was the motivation for that was actually driven a lot in many ways by this program. Cool. So it's already kind of a follow-up of the work that we did in this paper. So the observations are happening throughout cycle 2. So hopefully we are able to see that 4.25 micron feature again, or perhaps even some water ice. So that could be a really interesting validation of some of the hypotheses we forwarded in this paper. Nice. So that's one thing that's actually in the books already happening to follow up on this work. You can imagine also just following up more collisional fragments. So Euripides is part of a family, a whole family of objects. I can imagine just getting more of them. We know that they are related. It's one of the few cases in astronomy where you say this A and B are related together, right? We know exactly which members of that family are collisional fragments. We know that they had to have come from the same body. So looking at more of them can let us know whether this 4.25 micron
processes, right? Yeah.
Cool. And just kind of more generally, more data is always great. So, there's been a lot of work in the Kuiper belt in cycle 1. Over 80 objects were observed with JWST in the Kuiper belt. So there's been a lot of work trying to sort out the diversity in spectral shapes we're seeing there. There's several other papers that are, I think, in review that are going to touch on that. But eventually kind of grabbing all this data, synthesizing all the data from JWST from the first however many cycles, and then trying to do a much more careful look at these interrelationships. So I already suggested some trends, right? I think that figure 3, which shows the 3 micron band attenuating from the KBOs to centaurs and Trojans, that's the type of ensemble studies that you could do with 100 objects, right? You start to be able to do statistics, doing dynamical modeling, really doing the careful work of asking whether or not this type of scenario is feasible. So there are many observations in cycle 1. There are other programs in cycle 2 looking at KBO, in cycle 3, there are other programs that have been approved to look at KBO. So there's going to be more KBOs, many more KBOs coming in. So
cool.
So I think we're slowly collecting this big pile of data to then sort through in future years. So yeah.
I like that time scale. I like that
Yeah.
time scale.
Yeah.
So, yeah, I'm really looking forward to seeing this field develop over the next couple of years with all the data coming in. We get enough where you can start piecing together a coherent story. Very cool.
Yeah.
Ian, thank you so much for walking us through your very lovely article once again.
Yeah, thank you.
Yeah. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.